All right, students, we're back together again for the second part of our class this morning. If you'll take your books, you should have them open. Turn to page 366. If you take and turn to page 366, have something then maybe to mark in your book, or if you're taking notes on some things as we go through the lesson today. And we're going to be talking about electric generators, and we're talking about electric motors, AC and DC motors. And we're going to talk about generators today, and they're very similar to, and operate very similar to a motor, AC motor or DC motor. But we're going to see a little bit of difference here between them. Now, if you look at your book on page 366, you'll see where it says then mechanical motion, italicized letters there. Mechanical motion has can directly produce electricity. Produce electric current by the magnetic force that it has. The ability then of the magnetism to convert into mechanical motion into electric current is called electromagnetic induction. We talked about electromagnetic induction in some previous lessons there, but you'll notice then I've got a few things on the board here again this morning. If you look with me, talk about primary purpose of generators. And two things that work together to produce electricity in a generator. One is a magnet, as we know, the other is electricity. Now, motion then is magnetism plus electricity. That creates motion. We can create motion through there. That's where our generators come in. We have two, the DC generator and the AC generator. And there's some differences there. Of course, in a DC generator, you have a commutator, just like you do in a DC motor, to convert then the electron movement back and forth to get an alternating current. In a AC generator, as you know, similar to the AC motor, you have what is called slip rings. That just kind of keeps the wires then from getting twisted as they go through there, but they automatically have an alternating current. So the same things apply to the generator as to the motor. Notice I've written here the difference between a motor and a generator. A motor then uses electricity and magnetism to produce motion. We know that. Example of electric car, I'll talk about that in a moment. A generator then uses magnetism and motion to produce electricity. So they're kind of opposites in that way. Notice on page 366, if you're there, it says in the second column, a device that uses electromagnetic induction to produce electricity is a generator. And that's what we're talking about here, a generator. Now, the value of it, look at page 367. With the invention of the generator, you see in italicized letters, the invention of the electric generator made the production of large amounts of electricity practical. We can produce then large amounts of electricity through a generator and store that and move that to areas that we would need it. We work that way across our whole country. And electricity is transferred even to your homes by means of being able to generate this electricity and to store it. We talked a little bit about the AC generator already. It has a field magnet and it has slip rings, and of course it has its source. And you see an illustration on page 367 of a simple generator and how that operates. Notice that it has the same thing. We have a source there. You have your permanent magnet or your field magnet, just like you do in a simple motor. And then you notice you have the drive belt there that's turning the armature. And then you have the slip rings at the bottom there to keep those wires that are going against those brushes there from getting tangled up. And it's the same process basically with a generator. If you turn to page 368, and you'll see as we look at the bottom of the page, you see a AC generator. That is a power plant, and they're using this same method as a simple generator, of course, in a large capacity, a lot larger magnet, a lot larger components to it, and it generates huge amounts of electricity. And so we can use that to power our country, basically, and use them to power your home. Notice then you have on page 368, talk about the DC generator. We know the difference. The difference of DC is direct current. It has to be converted to an alternating current by use of a commutator. We have talked about that same thing in a DC generator. The same process then is used then to get this electricity generated and stored. If you look at page 369 there, notice the italicized letter. It says a motor uses electricity to produce movement, whereas a generator uses movement to produce electricity, which we covered here already. I would underline that in your book. Make sure you understand how that works, and then make a note of it there. And so now go back to page 368, and you see a car up in the right-hand corner of that page. You have an illustration of a car alternator. Now, our cars it operates on the same process. The source is the battery. Once that battery then gets the car started, the alternator then produces electricity and puts it back into the battery. That's we are able then to start our cars and operate the lights and all those things that are in there, but it has to put electricity back into the battery, and to keep that going, the battery operates a different way. We've talked about that, and the electrolytic cells that are in there and how that works. We'll mention that maybe in a moment, but the car alternators is a good illustration of electricity and motion then, and how that works in our car. If it didn't, you wouldn't get very far. You'd only go as far as your battery would operate that car, and then your car would, when the battery is run out, your car will be wherever it is until it's charged back again. So that's a good illustration there of that. Now, another way to produce electricity I've got up here on the board. Let me go back to here just one moment. When we talked about using electricity and magnetism to produce motion, the electric car is a good example of that. In an electric car, you have an electric motor on all four wheels, and that electric motor powers those wheels, causes those wheels then to turn and puts them into motion. And each wheel has its own electric motor, and it spins, and then that is generating electricity as it goes through there. When it stops, when you let off the gas, then that actually puts that motor in reverse, and it is generating power that goes back into the battery. The battery's in that electric car to build it up. Now, you still have to charge, of course, your car, because the stopping part, which regenerates and puts electricity back into the battery, you're only doing that very infrequent times. Most of the time, instead of slowing down or putting your foot on the brake, you're then putting your foot on the gas and trying to get your car to go forward. So it still needs to be charged. Electric cars still have to be charged. We worked that out where they don't have to be. It'd be a great invention, and they're working on ways to do that even as we speak. Let's go ahead and move on. Another way then, which I have here, another way to produce electricity is by what is called MHD, magneto-hydrodynamic generator. All right, that's a big word, big words that for that, but it is called a magneto-hydrodynamic generator. An example of that, and it uses an electrolytic solution. Right, that solution that has electrolytes in it, or electrons, and they can be motivated. An example of that is salt water. Salt water has, as we know, is able to conduct electricity and cause movement. Now, I kind of broke this down a little. The magneto part is a magnet. Hydro means water. Dynamic, of course, is movement. And so we have in this other source, if you look at on page 369, you have that use of the MDH, or the hydrodynamic generator that produces it. And it runs, basically what happens is they run water through there, and it charges those electrons that are in there. They keep moving, and then it produces that motion along with the magnetic and electric magnetic charge. It produces then electricity. That water then goes, charges push the electricity kind of through that magnet, and it produces that motion that gives us electricity. Now, not a very practical way to produce, at this point in time anyway, to produce electricity, because it takes a lot of water. You got to have a lot of salt water if you're using this solution, and then it needs a lot of magnetic power in order to do it. But they're working on things. There's no basically moving parts here in this way of producing that electricity, so it is valuable to us, but we're not quite there yet on being efficient in using that. Notice on page 369, let's read this last paragraph on the right-hand column. It says, MHD generators have the advantages of being simple and having no moving parts. Unfortunately, MHD generators do have some drawbacks. They are efficient only if extremely powerful field magnets, generally superconducting electromagnets, are used. In addition, to obtain much current, the flow velocity must be very high. In most MHD generators, the flow velocity is several thousand kilometers per hour, using a plasma as a fluid. Because of these drawbacks, the MHD generators are not yet used for practical power generation. So for the two things that are necessary, of course, you've got to have strong magnets, and then you've got to have that water moving at a very high speed. Your book says several thousand kilometers. That also means several thousand miles per hour that it would have to move in order to generate then some electricity that would be usable and practical for us. If you'll go ahead and move to page 370, we'll look there. We want to talk about alternate energy sources. We talked a little bit about this before. As you look there, some of them are listed there in your book. We have steam power plants that we use today. Use steam, and that steam forces wheels to turn and motion, which generates electricity. We use those all over the country to produce then electricity. We've talked about hydroelectric power. I'd underline that. I'd underline steam turbines and hydroelectric power in your book. And that's where they usually have the water dammed up, use a large dam, and use the water that flows through there that then turns turbines and produces electricity. And also, as you see in the pictures there, you have wind power, the big turbines, and solar power that is used then to turn those things that God's given us naturally. There are natural sources here that He's given us to be able to, for us to figure out how we can use them to better our lives in our country and around the world. And we've used some of those, and some of those things there. Those are alternate sources. When we can figure out how to use those in great efficiency, say solar power, then we'll be able to use those things in place of what we use now are fossil fuels. They are more efficient, and we can produce a lot more electric power by using fossil fuels. But a couple of things there, like in the case of nuclear power, which we use today, there's the problem of what to do with the waste, and it's toxic. And We have to take care of those things in certain ways, but there is danger there in that source. Using coal, another means by which we generate a lot of power that we use in our country, the emissions that it had, those are toxic. So we have to deal with those. And so we need to be working on more efficient ways, and we are working on more efficient ways to our country to provide then the energy, electricity that we need. A couple of reasons, and the one is we just talked about, they can be dangerous. The second thing is fossil fuels are going to run out one day. We're going to run out of fossil fuels one of these days, and so we'll need an alternative source for that, and they're working hard on those things today to provide the things we'll need in the future. Last thing I want to talk about, if you look with me here, is voltage, and that is transformers. Now what a transformer does, a transformer then, let me get right here, transformer then transforms current from one voltage to another. There's two types then. If you look at your book on page 371, if you look there, notice what it says about transformers. It is often necessary to increase or decrease the voltage of electric current. And so, such a change can be made by a transformer, a device that increases or decreases voltage of alternating current using electro and magnetic induction. In its simplest form, a transformer consists of an electromagnet wrapped in a second coil of wire. Notice that the illustration you have at the bottom of the page, and you see there you have it's called step-up transformers and step-down transformers. And you'll notice that the wire then on one end, there's more wire on one end than there is on the other. And then that's in a step-up transformer, which pushes more current through to get the electricity to the place that it needs to be. So transformers that step up, then the voltage and the current goes down. When the voltage goes up, the current goes down, and it pushes that current, that voltage through there to get it to places in other parts of the country from the power plant. And then if you look at the step-down transformer, you see that the output is less because there's less wire wrapped around the top of that magnet, as you see there. So one puts out more voltage, and the step-down puts out less voltage. So, so if you look with me at the board one more time, as we talk about this, step-up transformer increases the voltage and decreases the current. A step-down transformer decreases the voltage and increases the current. So here's what happens. With power, it goes from the power plant to the power lines to our homes or to industry, however, wherever that needs to go. And they need a lot of power. That's the step-up transformer to get that power from the power plant to wherever it's going over a distance. That goes through our telephone wires that we have across our, not telephone wires, but to the power lines that we have across our country. And then when it gets to, say, a neighborhood or a subdivision, you'll see transformers, which are those little gray kind of looking, blackish gray round cylinder things that are on the power line poles. And when it gets to that transformer, it reduces it then. It steps down the power so it can go into to 100, say 120 volts, that then goes into our house and we get 120 volt power, so we can use it in our house. So it has to go from, we have step-up transformers and step-down transformers that we use, of course, in all of our daily lives. So that is what transformers are used for, and you've seen those on power lines and poles there that reduces then right in our neighborhood to get power so that we are able to use it. All right. Go to page 372, and you'll see an illustration of that. there. You see, as you look there, where power comes from, the dams, and it goes into the poles. In the poles, then you'll see an illustration of a step-down transformer right there in the middle, and then it goes. You see one on the pole there, which steps it down to 120 volts and into our home, so we can use that. That's how that process works. And so we are about done with chapter 15, and we'll be moving on then in just a little while. Good to be with you again this morning. Hopefully this is helping you as we go through the chapter, and we'll be testing on this in just a short while. So finish the work that I've left for you, and we'll be talking to you soon. Have a great day.